All right, this final section here of chapter 1 of our calc material is on infinite limits, and we'll start just by looking at a concrete example so you guys can get a visual. By the end of this section, we'll move away from visuals and graphs of these functions, and you will be able to do this analytically. But just so we have an idea, I'm going to start by looking at this first one here. Consider this function f of x, which is 5 divided by x minus 1. So if we break this function down, we know that this function has a discontinuity at positive 1, because if we plug 1 in down here, we would get 5 divided by 0. We also know that if there is an essential discontinuity at 1, that means there's a vertical asymptote at 1. And then if you can think back to Math 3 and earlier this year, thinking about the parent function 1 over x, this is a transformation of that function. So we know that 1 over x behaves like this. Now this is just a sketch, but this is enough for us to talk about limits of this function. So when we look at these two limits here down below, we're asked to find the limit as x approaches 1 from the right and as x approaches 1 from the left. So when we think about x approaching 1 from the right over here, we can see that as x gets closer and closer to 1 from the right, this function will reach infinite values. It continues approaching greater and greater y values. So what we would typically do is write that this approaches infinity, which is true. And then if we look at the same function, but as x approaches 1 from the left, so again, from the left is indicated by that little minus after the 1, we can see that this function very quickly starts to approach negative infinity as x approaches 1 from the left. So this is what we would write. I do also want to add a third limit here, because right now all we've got are limits from the right and the limit from the left as x approaches 1. So let's talk about the limit as x approaches 1 of f of x. So think about this. It's fine for us to talk about the limit as x approaches 1 from the right or as x approaches 1 from the left. But think about what happens as x approaches 1. So I'm not specifying coming from the right or the left. It's just 1 in general, because that is unbounded behavior and it's different. So really two reasons here. First of all, the behavior is different from one side to the other, and it's unbound, meaning it is approaching infinity or negative infinity. That means that this limit as x approaches 1 does not exist. So I just want to clarify that oftentimes we might not be able to discuss the limit as x approaches a specific value in general, but you could break it down on the right and the left. So now we're going to talk about what it means if we are looking at an infinite limit. So this definition here in the box is very straightforward. It's an infinite limit if the limit of a function as x approaches some value c is positive or negative infinity. So this is what we would have said in the past, and it's true. However, it doesn't indicate the existence of a limit just because we put positive or negative infinity. In fact, an answer of positive or negative infinity actually means that the limit does not exist. So this next note down here below is super important to think about. So if we have the limit of a function equaling negative or positive infinity, it does not mean the limit exists. In fact, it means the limit fails to exist. And writing positive or negative infinity just clarifies why it doesn't exist, and that's because the behavior would be unbounded. So this positive or negative infinity answer just means it doesn't exist because it's unbounded. So that's just some clarification I wanted to make, because even at the beginning of the year when we were talking about limits, we did write that answers were positive and negative infinity for certain limits, which is fine. But it's important now we kind of look at that more closely and recognize that that means that the limit actually fails to exist because it's unbounded. Okay. So we'll start in these first two examples by looking at graphs. By the end of this, we will not be relying on graphs though. So we're going to have to think about this numerically. But we do know enough about some of these functions that we can sketch a quick graph. So in number 1, we're looking at the limit of 3 over x minus 2 as x approaches 2 from the right. So I'm going to stop right there because we know that as x approaches 2, looking at the denominator, 2 is where this essential discontinuity is. That's where the vertical asymptote is. Now, do we know what's happening as x approaches 2 from the right versus the left? So maybe some of you are visualizing this graph, and if not, that's okay, because we're going to do it without graphs later anyways. But we do know we've got this vertical asymptote at 2, and this graph behaves much like the one we just did. So we can see from just visually that as x is approaching 2 from the right, this function is approaching positive infinity. So we can just say that this equals infinity. So which is really telling us two things. It's telling us that the limit doesn't exist, specifically because it's unbounded. Instead of writing does not exist, we can write infinity. That's the correct answer. But it's specifically denoting why it doesn't exist, and that's because it's unbounded. I'm going to do number 1 again. I'm going to do it analytically this time, the way that I'm going to expect you guys to do it eventually on your own. So without thinking of this as a graph, we cannot, our first strategy early on in this chapter was, our first strategy was direct substitution. That's like the number 1 best option if our function is, air quotes, I'm using air quotes, well behaved. So remember, this function is not well behaved at 2, meaning it's discontinuous when x equals 2. So that takes away our ability to use direct substitution. But we can think about what happens with direct substitution as x approaches 2. So first of all, we can break this into 2 separate limits. We've got the limit of the numerator and the limit of the denominator. So I'm going to kind of do this again. So the limit of 3 as x approaches 2 from the right. So I'm just talking about the limit of the numerator. The limit of 3 as x approaches 2 from the right. 3 is just a horizontal line, and the limit of 3 as x approaches anything is always going to be 3. Now let's think about the denominator. So I can't directly substitute 2 in for x right here. But I'm going to draw a little number line here for you. Okay, so thinking about the value 2. So we're breaking things down, real simple idea here. I'm looking at 2 on a number line. Now let's think about what happens as x approaches 2 from the right. So x is getting closer and closer to 2 from the right. Then think about the denominator of our function. I'm talking about the limit as x approaches 2 of x minus 2. So think about x getting closer and closer to 2 from the right, and then subtracting 2 from that number. So that would mean 2 minus 2 is 0. So as x approaches 2 from the right, and I subtract 2 from that, let me change colors here, hold on. Okay, I have no fun colors, that's boring. Sorry. Alrighty, if I subtract 2 from that, then my new number is actually approaching 0 from the right. So here's how I write that. I write that as 0 and then a little plus sign. So I'm not going to circle this in because this isn't my final answer, but here's what happens when we break this down analytically. I'm going to kind of repeat myself. The limit of the numerator is just 3 itself. The limit of x minus 2 as x approaches 2 from the right. That's why I drew this number line here, because as x is approaching 2 from the right, when I subtract 2 from that, because that's what's in my function, x minus 2, then really my result is approaching 0 from the right. So think about what that means. I'm taking 3 and dividing it by a number that's getting very, 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 very small, but it's positive. So that's what this plus, it's approaching 0 from the right. So think about what happens when you take an integer, a positive integer, and divide it by a very, very small positive decimal or fraction. So when we divide by a small number, what we're really doing is seeing infinite growth. And I would challenge you to even just grab your calculator and do 3 divided by 1. Obviously that's 3. 3 divided by 0.1 is 30. 3 divided by 0.01 is 300, and so on. So what happens is this, as x is getting closer and closer to 0 from the right, this function is 3 divided by this really small number is approaching infinity. So what we did here, the first time we looked at this, we're looking at the visual graph where it's very clear that the answer is infinity. Now we're thinking about it analytically. My numerator is always 3. The denominator, as x approaches 2 from the right, approaches 0 from the right, which means I'm dividing 3 by a very small positive number. When you divide by a tiny decimal that's positive, the result is very large. So this is that analytical piece of it. Okay, so let's look at number 2. All right, so number 2, we've got another rational function, meaning it's in the form of a fraction. So this function definitely has the same kind of theme here. We've got a discontinuity at 1. I could sketch a graph of this, but I want to think of it analytically first, and then we'll go look at the graph. So let's think about this function if we break it down into 2 separate limits. So similar to the way we thought about number 1. So what I'm really thinking about is the limit of x minus 3 divided by the limit of x minus 1. But I'm looking at each of those limits as x approaches 1 from the left. All right, so when we look at that, we have the numerator, which is the good news about this. This function, x minus 3, when we break it down, this is well behaved for all x values. And I can just directly substitute 1 into that because this is in the numerator. I don't have any issues here. So I can just plug in 1 in for x and do 1 minus 3. Even though it's saying from the left, remember, I can, no matter if it's approaching 1 from the right or the left, we can still use direct substitution here in the numerator. So that would just be -2 in the numerator. The issue comes with the denominator because when x approaches 1 in this denominator, 1 minus 1 is 0, and then I would be dividing by 0, which is typically an issue. But because this is one-sided, I'm approaching 1 from the left, we need to think about the result, which is definitely approaching 0. What is that going to do to this result when I divide -2 by this decimal down here? So again, if it helps to draw the number line, draw the number line. So we're looking at as x approaches 1, so here's 1. When I subtract 1 from that, I'm at 0. So as x approaches 1 from the left, meaning from the left, so think about as x is getting closer and closer to 1 from the left. If I subtract 1 from that, and I'm going to think of subtracting 1 because that's what my function is up there. If I take it and subtract 1, then my number is approaching 0 from the left. So what does that mean? It's negative, but it's a tiny decimal that's negative. So what we have as a result is -2 divided by this negative, infinitely small negative number. So think of like -0.000000 and then some number. 2 things are happening. We've got a negative divided by a negative. Those are going to cancel out. to be a positive, and then you've just got 2 divided by an infinitely small number, and that is going to result in an infinitely large number. So this results in a limit of infinity, which means the limit doesn't exist because it's unbounded, approaching infinity. If we wanted to look at the graph of this to confirm our result here, I'll just do a tiny little graph down here. So this graph has we know it's got a vertical asymptote at 1. And it also has a horizontal asymptote at 1. And this is going back earlier to the year because the leading coefficients are both x, and if they're the same power, those 2 leading coefficients, you just take their coefficients divided by each other, which would be 1 over 1. That's old stuff. Don't worry if you've forgotten it. This function behaves like this. Okay, so we can see visually if you had grabbed your calculator and said, okay, here's my function, what's happening as x approaches 1 from the right, you can just visually see right here, as x approaches 1, it's going to go up higher and higher towards infinity. But this analytical way of doing it is what we're moving on to. So we know how to do it with a graph. Now, we're going to have this no calculator portion where we're doing this analytically. Okay, so before you move on and get some more practice, if you're feeling a little confused or unsure, that's fine. This is a tough concept, and I expect, these first couple of problems to kind of leave you like, huh? Oh, look, I have a little arrow here. Oh, this is so cool. I'm finding all these new exciting things. Okay, I have cute little arrows now. Definitely going to use those. Okay. All right, so before we jump in with more examples, let's revisit vertical asymptotes, because those vertical asymptotes are where you're going to have these infinite limits. So just to recap on what a vertical asymptote is. Oh my gosh, you guys. There is a lightsaber pointer. That is a lightsaber. I can even change the colors. That's amazing. Okay. So as x approaches positive or negative infinity, no, if f of x approaches, I'm just distracted by this lightsaber, but I'm going to get over it right now. Okay, if f of x approaches positive or negative infinity as x approaches c, then it's got a vertical asymptote at c. So this is just recapping what we already know about vertical asymptotes. And now we'll just practice finding vertical asymptotes. Again, it's those essential discontinuities. And this is nothing new, just reviewing essential discontinuities. Those are the discontinuities that are not holes. Those are the vertical asymptotes. So, and it's always, in the case of what we're familiar with, it's always been where these denominators were equaling 0. So the essential discontinuity would be where 3x minus 1 equals 0 in this first example. So you would just set the denominator equal to 0 and solved. So this had this example number 3 has a vertical asymptote at x equals positive 1/3, because you would add 1 and then divide by 3. With number 4, we're looking over here, and again, these essential discontinuities that result in vertical asymptotes is where these entire denominators would equal 0. So x squared minus 9 equals 0. You should hopefully recognize that this is going to give you 2 different x values. So this function has 2 vertical asymptotes. If you add 9 to both sides, you get x squared equals positive 9, which means you get vertical asymptotes at positive and negative 3. So make sure you're cautious about those quadratics in the denominator, because they result in 2 answers for x. Number 5, if we look at the denominator here, obviously that just will equal 0 when x equals 0. So this has the vertical asymptote is just at 0. And number 6 here, again, yes, there's a quadratic in the numerator. However, the vertical asymptote is always determined by the denominator, so really we just want to know when x squared minus 3x plus 2 equals 0. So, whoops, not 20, equals 0. This would need to be factored in order to find that out, or you could just use the quadratic formula. If you're factoring it, doing the diamond game or area model, we would put 2 here, negative 3 here, and we want these two numbers to be the two values that multiply to 2 and add to negative 3, which would be negative 2 and negative 1. So, and because this leading coefficient is just 1, that's how these negative 2 and negative 1s, that's exactly how this factors. And you can always double check. X squared minus 1x minus 2x, that's my negative 3x. And then negative 2 times negative 1 is positive 2. Okay, so just doing a quick check there. That means my two vertical asymptotes are at 2 and 1. Okay, so that's just a quick recap on finding where those vertical asymptotes are. All right, so let's flip the page and kind of recap what we've done and look at a few new properties of limits and wrap things up. Okay, this box we're going to fill in here with these properties of limits. I do want to break down the circumstances that it's laying out for us. So the first is that we've got a limit of f of x. X is approaching c in both of these. X is approaching c, x is approaching c. The limit of f of x, if the limit of f of x is infinity, and the limit of g of x is L, meaning some real number. And then we're going to look at what happens when you combine those two separate limits. So let me just show you a quick example, and you don't even necessarily need to write this down. But let's say I was doing like the limit of g of x divided by f of x, so two separate functions as x approaches c. So if it's the case that I know that the limit of g of x is, because I was told, some specific value, so L, divided by infinity, because I know over here the limit of f of x is infinity, then think about what that would mean. I'm taking a real number L and dividing it by a number that's approaching infinity. You know, if you take any number and divide it by something that's getting larger and larger and larger and larger and larger, basically that whole thing is going to approach 0. So we've got these different situations. If I'm like this one that I just did, I gotta switch my pointer. I'm just too distracted here by my lightsaber. Okay, my arrow. Okay, so this situation here is matching up with this third one down here. So there's other operations. So we could have added or subtracted L and infinity. We could have multiplied them. Or divided. So that's what we're looking at, because when we've got complicated limits, like if I'm looking at the limit of some complicated function, maybe I have 3x times 2x plus 1 divided by sine of x, you know, all these different things going on, then we're going to be breaking this down. I have several different individual limits, and if I can find their individual limits, then I can find their combined limits. So that's what we're kind of breaking down here. Okay, so again, our situation right now is if the limit of f of x is infinite and the limit of g of x is some real number, then when if I'm finding the limit of f plus or minus g of x, what I'm really doing is taking this infinite limit and adding or subtracting the limit of g of x, which is some real number. So think about it. If you're at infinity and you subtract some number, the result is still infinite. Same goes if you're I can't remember if I just did adding or subtracting. Regardless of adding or subtracting, if you've got an infinite number and you add or subtract a real number, you're still at infinity. So this one's pretty easy to follow, because what you're doing here is taking infinite values and adding or subtracting a real number results in infinity still. Okay. Then we have, what if I was looking at a function that was the product of f and g? So if you think about taking the limit of f of x, which is infinity, positive infinity, and I take it and multiply it by the limit of g of x, which is, well, in this case, L is what we'll say it's greater than 0. So it's a very, it's just a positive real number. Again, we're at infinity. We multiply that by some positive integer or positive real number. We are still at infinity. But think about it, if L is less than 0, I've still got infinity times some negative value. That would mean I'm taking a positive number and multiplying it by a negative number. But my positive number is infinite, and when I multiply that by a negative real number, the result would be negative infinity. So a lot of what we're going over right here is just logic in number sense, understanding infinite values, understanding how infinite values are affected by combining them with real numbers via combining them via plus or minus, multiplication, or division. Okay, and then this next one here is if I know the limit of g of x is some real number, the limit of f of x is infinity, that's what I did over here. So that means when I'm finding the combined limit of g over f, what I'm really doing is taking a set real number, some specific real number, L, and dividing it by an infinitely large number. And you know that if you take any real number and divide it by something that's growing larger and larger, you're dividing by that larger and larger number, meaning the whole quotient, this whole value, is going to approach 0. So hopefully none of this is surprising or confusing. If it is, give it time to set in. But this is again just understanding the way numbers work, especially infinitely large or small numbers work. All right, so let's apply this to some concrete examples. And with these examples, these last 5 problems here, these are all kind of like, these are all no calculator, by the way. And kind of like this end kind of like analytical, these are kind of like the most complicated of the analytical limits we'll be doing without a calculator. So again, if we look at some of these functions, like number 8, there's a lot going on here, and that's why we're going to break it down into multiple functions. Same with number 7. So we're looking at the limit of 3 plus 1 over x. I'm going to break that down into 2 separate limits. So let's think about that as the limit of 3. So the limit of 3 plus the limit of 1 over x, and both of those have x approaching 0 from the right. Okay. So the first piece of this, the limit of 3, we know that the limit of 3 as x approaches anything is always going to be 3. Then I can just find the limit of 1 over x as x approaches 0 from the right, and I'll add that to 3. So let's think about that. So as I think about this limit right here, we know that we cannot directly substitute x or 0 in for x because then we have this undefined value. But x is getting closer and closer and closer and closer to 0 from the right. So what we're really doing is taking this real number 1 and dividing it by a number that's infinitely small, getting closer and closer to 0 from the right. So again, we're taking 1, dividing it by a very small positive decimal value. So that's going to result in an infinitely large number because, again, it's that same concept of taking 1 and divide it by 0.1, that would be 10. 1 divided by 0.01 is 100. 0.001 is 1,000. So we see this number getting very large very fast. So what that means is we are down here in our actual answer, we've got 3 plus infinity. So this final result, is 3 plus infinity, which is why we had some of these properties up here, if I have a real number and I add infinity to that, the result is still infinite. So number 7 here has a limit of, infinity. All right, let's look at number 8. Okay, first to clarify what's going on here, we've got multiple functions here. It's hard to tell what's going on. This denominator of the first big function, we've got x squared plus 1 divided by this function 1 over x minus 1. So the first thing we're going to do is let's break this down into simpler ways to think of it. I'm going to think of this as the limit of x squared plus 1 divided by the limit of 1 over x minus 1. Okay, both of these are the limit as x approaches 1 from the left. All right, focusing on the numerator first. This function, x squared plus 1, we're just looking at that as its own function now. X squared plus 1, it's in our numerator. It's well behaved at 1, so we can just use direct substitution here. So when I plug in 1, this is positive 1 from the left. It doesn't matter what direction I'm approaching 1 here. When I square it and then add 1, my result through direct substitution is just 2. So my numerator for my whole limit is 2. Now let's look at the limit of the denominator, 1 over x minus 1. We know that this value of 1 is problematic in our denominator. That's because 1 minus 1 is 0. So I'm going to think about, what we're doing is breaking this second function, this denominator, into two. We can think of it as two limits as well. The limit of 1 divided by the limit of x minus 1. So we know that the limit of 1 is 1. And the limit of x minus 1, that's the problem area because I can't directly substitute 1 in there. But I'm approaching 1 from the left. So this is where I'll draw the number line if that helps. So here's 1, and we are approaching 1 from the left when we subtract 1. So if you subtract 1, you end up approaching 0 from the left. So what you have is 1 divided by a very small negative number. So negative, think about infinitely small, 0.0000. What you're doing is you're going to compute a value that's this whole thing right here, 1 divided by some infinitely small negative number. That's going to be a very large number. And because of this negative, it's actually going to be a very large negative number. So again, right here, we've got 1 divided by, okay, I hesitate because I see this negative next to my 0. Why is this not erasing? Okay, I can't erase. I don't know why I cannot erase that. All right, I'm going to put this little, this is approaching 0 from the left. So I'm going to back up for a second. Right here, I've got, when x was approaching 1 from the left, and we subtract 1, then we're approaching 0 from the left. And I accidentally wrote negative 0 here. So that was my bad. What I really meant was to write 0 from the left, meaning I'm approaching 0 from the left-hand side. Yes, it does result in these negative numbers, but negative 0 isn't like a real thing. Okay, so that results in a positive number divided by a negative number. That's the negative aspect of it. And then this real number, this real positive number divided by infinitely small decimals is actually approaching infinity. So the result is 2 divided by negative infinity. Wow. 2 divided by negative infinity. So now we have to think about what 2 divided by a negative infinity is. So we're taking 2 and dividing that by an infinitely large negative number. So this number is getting bigger. Well, it's negative, but the negative number is getting more infinitely negative. So we're taking 2. Think about 2 divided by negative 100, 2 divided by negative 1,000, negative 10,000. That number is going to level out and get closer and closer to 0. All right, moving on to number 9. Okay, another function here that is in the form of a fraction. And again, I'm going to break it down into 2 different functions. So I've got the limit of x squared divided by the limit of x squared minus 9 as x approaches 3 from the right. So when we break this down into numerator and denominator, we can directly substitute this 3 in for our numerators. So we can, it doesn't matter if x is approaching 3 from the right or the left with x squared, because it's our numerator, we can just directly substitute that in and it would be 9. The denominator is where we have a problem here. So this function is not defined at 3 because when you square 3 and then subtract 9, the result is 0. So I'm going to put this 0 here. That's undefined, but x is approaching 3 from the right. So thinking about that, if I've got a number line, here is 3, x is approaching 3 from the right. So when as x approaches 3 and I plug it back into this and I square it, and that would get 9, and then I subtract 9, so 9 minus 9 would bring us to 0, and x is now approaching 0 from the right. So we have to think about not just the fact that it's 0 down here, but it's approaching 0 from the right. So now we've got this 9, a real number, divided by an infinitely positively small number. So a decimal that's really, 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 really tiny but positive. So 9 divided by this infinitely small number will result, as we're starting to figure out, in an infinitely large value. Okay, these last few examples, or 2 examples, have trig functions in them, which is super exciting. Okay, so don't freak out yet, because we're still going to treat these the same way we've been treating the others. So we're looking at, in number 10, the limit of 3 cotangent of x as x approaches 0. So before we even get all flustered about cotangent, let's just rewrite this as the limit as x approaches 0 from the right. And 3 cotangent. Remember, cotangent is just the reciprocal of tangent. So cotangent is 1 divided by tangent. So I could rewrite this whole thing as limit of 3 divided by the tangent of x. So then we can kind of visually see this a little bit better. I can take this as the limit of 3 as x approaches 0 from the right, which is just 3, divided by the limit of tangent of x as x approaches tangent of x as x approaches 0. Okay, you do need to think, because this is no calculator, you can't plug in some values to figure out the tangent of x. You could maybe rely on your unit circle, but also hopefully just rely on what you guys remember about the tangent function. This is a function you've seen a little bit, and I'm hoping you could at least remember that our interest here is as x approaches 0. The tangent function when x is 0 is actually 0. How would I know that if I'm not sure? Well, tangent is sine over cosine, and if x is 0, I haven't rotated at all around my unit circle, so I'm at 1, 0. That's terrible writing. How can I make this nicer looking? So this ordered pair is 1, 0. The tangent of 0 is sine over cosine, which is 0 over 1, which is 0. So tangent of 0, all I'm doing is just reiterating why tangent of 0 is 0. So what this means is I've got 3 divided by 0, which is a problem because 3 divided by 0 is undefined. However, if we kind of sketch in this tangent function, and remember that this is saying x is approaching 0 from the right. So if x is approaching 0 from the right, getting closer and closer to 0, look at what's happening to our function. It's approaching 0 from the right as well, meaning, so let me just denote that, it's approaching 0 from, whoops, I need my pen, the right, meaning it's positive, but getting really close to 0. So now we can kind of think about what this would end up being. 3 divided by a very small positive decimal is infinity, positive infinity. So you don't have to remember too much about your trig functions other than maybe a couple points from the unit circle and a quick visual of the graph. Sine, let's move on to 11 because you're probably all a little more familiar with sine. So in number 11, we're looking at the limit of 2 over sine of x as x approaches 0 from the left this time. So again, we can break this down into 2 separate functions. So we're really looking at the limit of 2 divided by the limit of sine of x. The limit of 2 as x approaches anything is simply 2. Now sine of x is what we have to think about a little more analytically. So the sine function, so here's a couple ways you could think of it. Here's our unit circle, and we're approaching 0. So meaning x is the rotation here. So 0 degrees puts us at 1, 0, and the sine of that is 0. So if we just use direct substitution here, which we can't because we've got 2 divided by 0, but remember x is approaching 0 from, where's my pointer? From the left. So if x is approaching 0 from the left, and this is where it might help you to think of the sketch of the actual graph of sine. So if we're looking at the graph of sine, and you remember that the sine of 0 is 0, sine of pi halves is 1, so we know the sine function does that. So when we're thinking about x approaching, find another color here, x is approaching 0 from the left. So that means we're coming from over here. X is approaching 0 from the left. Look at my y value. The whole function itself is negative. So as x approaches 0 from the left, we're talking about the function values getting closer and closer to 0 as well. But they're also coming from the left, meaning those values are negative. So we've got 2 divided by this infinitely small negative number. So the negative number aspect means our answer is going to be negative because it's 2 divided by a negative value, but it's an infinitely small negative value. So think like 2 divided by 0.0000 whatever. That's going to result in a very large negative. So the answer for that is negative infinity. This section usually causes some confusion for some of my students, so I don't want you to feel panicked. If this feels confusing, give it some extra time on the homework. You're going to want to practice through those problems and then check your answers with my key. And hopefully by then it will feel a little more solidified, but it's definitely going to take some practice to feel comfortable with it. All right, before we totally end here, I do want to do one quick recap because we've seen so many different situations with limits. So if there's any space in the bottom right hand corner of your paper, you can just kind of mark off some space or flip it over and do this on the back. We're just going to do a quick limits summary. I'm not doing any exact like specific examples, but just a quick summary. Hopefully this will solidify a little bit for some of you and just recap this big picture of analyzing limits. So there's several different situations. We started chapter 1 with the situation, well, the ideal scenario would be direct substitution. And that would be wonderful if we could use that every time, but we quickly saw that we would not be able to use direct substitution every time. So then we had these other situations. So there was one situation where through direct substitution, we had a result of 0 divided by 0. That was an indeterminate value, and that meant we had to do a few things. One of the things we did was factor and simplify and like cancel out those common factors, and then you could use direct substitution. Or we rationalized the numerator, and then we could use direct substitution. So we did something to manipulate it. So I'm going to write do something, even though that's vague. We did something to manipulate the function, and this is all within the section 1.2. Then the next situation we saw was, maybe not the next situation, but if we had 0 divided by some number. So if we split it up into two functions, the limit of the numerator was 0, the limit of the denominator was some real number. 0 divided by a real number is just 0. Then we saw the reverse of that situation, which is the some number divided by 0. And this is going to relate directly to, like if we look back at number 11, we had 2 divided by 0. But remember, it's always as x is approaching a number from a direction. So it was always as x is approaching 0 from the left or the right. So from the right or the left. And in those cases, your answer was a real number divided by an infinitely small positive or negative number. So that was always negative, positive or negative infinity. We also saw, let me make some more room here, a couple situations where we might have had an actual number, L, divided by positive or negative infinity. And in those situations, again, let me see if I can find one that matches up with that. That would be similar to number 8. If you look up here, we had 2 was the limit of the numerator, and then the denominator ended up approaching negative infinity. Well, the result of a real number divided by an infinite number, regardless of that infinite number being positive or negative, is always approaching 0. So that situation of a real number divided by positive or negative infinite numbers is always 0. I think that's it. I mean, then we had some other basics like the addition and subtraction, like L plus infinity or plus or minus infinity, or multiplication. Those are a little more straightforward, but I just kind of wanted to recap these situations here. So this is it for chapter 1, just analyzing these limits numerically, not necessarily from looking at the graph. So again, this homework here is probably a pretty important one for 1.5 in thinking and analyzing and slowly going through these limits. So do not use your calculator in the 1.5 homework. You're going to need to be able to work through these problems without it. All right.